Okay, so let's start the class. We have chocolate today. There is a code. Check the code first. Okay, so remember, this is a easier unit. And then the next unit will be about conservation of energy. Chocolate, kosher. And then we have test number 3. So test number 3 will be online, right? I will open a window. And I didn't decide on the date, but it's coming soon. Okay, so keep an eye on that. Okay, so here we start. We were talking about work done. Okay, so far the force was constant, but sometimes it's not. So let's say, so for the final, okay. So you see here, if the motion, oh, I have to stop back. I'm sorry. We have chocolate here if you want to. Kosher. Chocolat Suisse. Okay, so you see here, if the displacement is along the x-axis, so the force can be a function of x. It means it can change with the position. And this is because, so first of all, you need to take the cosine in that case, right? So you have to take the component of the force along the displacement. And then maybe you're not going to pull with the same force, obviously. Okay, you're going to start strong to get it moving. So you need to overcome static friction, and then you're going to maybe pull at a constant force, and then maybe you're going to get tired. So we can get something like this. Okay, so here that will be the force as a function of the position, and we are talking about the displacement along the x-axis. So in that case, you have a graph. And if you want to find the work done by a force on the system, then you need to find this area. Is that clear? So the best example will be, we already talked about that, but will be, for example, so first of all, you have the work energy theorem, which you can show that it doesn't matter if the force is changing with position. Okay, the kinetic energy theorem will still be true, and we can show that here, right? So even though you take the integral because the force is changing with position, you can show using a little bit of calculus, not much, that the net work will be equals to the change in kinetic energy. Okay, you don't need so much calculus to show that. Okay, so we did that. And then in case of spring, okay, so in that case, you're going to have a restoring force. That restoring force is proportional to the stretch, okay, to the displacement, or by depends on by how much you are compressing the spring. Okay, so you see it's going to change with the position. So it's a varying force. Okay, we have chocolate if you want, and we were able to show. So that's what we did last time. So if you take your spring, you go from rest position and you're going to start to stretching it. Okay, the restoring force will increase. That makes sense? That's when you do Pilates, that's what's going to happen. If you multiply the stretch by 2, the restoring force will be multiplied by 2. So it's a linear relationship. Okay, so you have the force here, restoring force, or the spring force as a function of position. So to find the net work, all we have to do is to find the area, which is the base times the height divided by 2, or you can do it using calculus, and you see that the elastic potential energy that you are storing inside a spring because you are doing work on it. So you are doing work on it. That means you are transferring energy to the spring, and that energy is being stored into elastic potential energy. Do you agree? Right? So you are doing work. So energy is being transferred from you to the spring. That constant here is called a spring constant, and stiffer is the spring, larger is that constant. It depends on the spring. Okay, we already talked about that. Conclusion, I want to make something clear here. So potential energy for a spring. So we go from the configuration here. So this is the x-axis. So now it's happy because it's not being stretched. Now if you stretch it, okay, you are doing work against. So that means you are doing work against the restoring force, right? So the restoring force is going to increase, increase, increase. So the restoring force equals minus kx. Okay, and because you are doing work on it, you are transferring energy. Okay, and it's being stored inside the spring, and that will be called potential elastic energy. Agree? Okay, so far so good. Now I want you to see something. So potential elastic energy equals, I'm going to put as a, maybe as a one half. So it will be 1/2 k x squared. Okay, we have chocolate if you want. Can you take the derivative for me as a function of x? Huh? Kx. You're welcome, kx. Right? And what is kx? Yeah, so it will be so kx is the restoring force, right? So if you derive potential, you get the restoring force. And that will be true for any kind of potential energy, including gravitational potential energy. So each time you have potential energy, there is a restoring force that wants to bring the system to the lowest energy state as possible. So for example, if I do work against gravity, so everything happens like you have an invisible spring connected to the center of the earth, and it wants to bring that mass back to a lower level of energy. Okay, so there is a restoring force. So each time you have potential energy, you're going to have a restoring force. That restoring force is called a conservative force because I can always get back the energy I put inside. If I push something and you have friction, right, all the energy will be lost to heat and you cannot get it back. Do you understand? So anyway, any potential energy, when you derive, you're going to get the restoring force. Okay? So actually, you are missing a negative sign. So that negative sign means that the force wants to bring the system back to the lowest energy state. Okay? So now I can write that the restoring force, or any restoring force, if I stay up, that doesn't work. So the restoring force will be equals to minus the derivative of the potential energy. So in that case, you see you work only along the x-axis, but you can work also along the y-axis, along the z-axis, the three axes at the same time. So we say that the restoring force derives from potential energy. So what is that? It's the slope. Very good. It's a slope. Okay. So if I want to make a graph, okay, the elastic potential energy as a function of the position, what do you think it's going to look like, that potential energy? I should not put, okay, I'm ahead of myself here. Now that should be called potential elastic energy. What do I get? Look, the elastic potential energy. Okay, so what kind of graph is that? As a function of x? A parabola. Do you all agree? Okay, so the potential energy, okay, it's going to look like a parabola. It's going to look like this. Agree? And that will be, for example, I'm going to stretch out the spring up to a maximum stretch here. Agree? So I like that because you see how you can use calculus and math, and it's not very advanced. Now, at any point, you see the restoring force here. So the restoring force will be minus kx. So at a given point, the restoring force will be the slope. And there is a negative to show you that restoring force is pointing to the initial state. That restoring force wants to bring back the system to where it was before, to the lowest state of energy. So that's why we have a negative. So a slope usually show you, from a lower x to larger x, but here, because of the negative. So this slope is representing the restoring force. Isn't that beautiful? Interesting, yes.
That would be the tangent of the point.
Very good. Very excellent. Yes, yes. So in that case, that will be the tangent, right? The tangent of the parabola at that point. Which means if I want to connect and review, you see you have an angle here, that tangent here, the tangent of this angle will be the slope. Okay? Okay. Isn't that beautiful? So we're gonna make just a step forward, just to show you how we can apply that. So if you have the Earth, so the Earth has a mass m, and you have a mass m here. I don't know, it could be the International Space Station, for example, right, where 2 astronauts are stuck, sadly for them. So you see that, of course, there is a force here that will be the force of gravity, right? Wants to bring that mass to Earth. Agree? So this system has gravitational potential energy, because if the space station stops moving, okay, for some reason it's gonna hit the brake and it doesn't move anymore, it's gonna fall toward the Earth. So all that gravitational potential energy is gonna turn into kinetic energy. Agreed? That's how you wiped out 2/3 of species on Earth, right? 65 million years ago. What killed the dinosaurs? It's the kinetic energy, because you had potential energy to begin with. And kinetic energy is very deadly because it's proportional to the speed square. So that meteorite that killed the dinosaur had like 100 million hydrogen bomb equivalent. That was very bad. So anyway, it has gravitational potential energy. Okay, that gravitational potential energy, I'm going to put a minus, meaning it's binding. Each time you have a minus, it means it's binding. Okay, and it's the whole system that has potential energy. You're going to have a constant. Don't worry about that constant yet. That will be very small, just to signify that gravity is very small. You see, it's very easy to defy gravity. Look at that. You see how strong I am? I can defy gravity. So gravity is very small. It depends on the mass here, the mass of the Earth, And then it depends on the distance here. So this distance here, right? The distance between, and that's the genius of Newton. The gravitational law was developed by Newton. That's why he had to invent calculus before. And he kept everything as a secret. He didn't want to publish. And because at the time, if you want to publish, you had to pay. And he was not only a sociopath, but he was not very, he didn't like to spend his money. So he had to wait for his friend Edmund Halley to pay for his publication. But he was a super extra genius. Right? Okay, so how can we find the restoring force, which is in that case will be the gravitational force? How do you go from the potential energy to the force? You need to take the derivative. Very good, very good. And how do we take the derivative of 1 over r? Huh? So what?
That's
Yeah, okay, so you take the integral of 1 over r. What do you get?
yeah.
No. No, sorry, you're right. No, I made a mistake. You want to find what? The integral? What is that? Does it say? The restoring force equals what? The derivative, sorry. So what's the derivative of 1 over r?
1 over r squared.
Very good. 1 over r squared minus 1 over r squared. Do you agree? If you don't agree, go to Wolfram Alpha. No, go to Google and say derivative of 1 over x. It's going to say minus 1 over x squared. So you see the restoring force, it's like an invisible spring trying to bring back that mass here closer to Earth. And you find this restoring force by taking the derivative. Sorry, I have to focus. Let's focus. So that will be plus what? Help me. G times lowercase m, and here I have square. Very good. So you see, this is my gravitational force. Okay, the force due to gravity. And it makes sense because in magnitude, as you move away from Earth, the force is going to decrease. You don't expect it to stay strong forever. At some point, you're going to escape, right? At some point, you're going to reach the edge of the solar system at some point. So you can escape gravity if you have enough kinetic energy. So that you could have guessed it, but there is a square because it's called the inverse square law. It's very important in physics and engineering. Each time you have a source, like you have a source of light, for example, or a source of radiation, like uranium, okay, it's going to emit radiation in all directions. Are you with me? Or a gravitational field will behave like light, or an electric field, okay, the strength, because your energy is going to spread out over a larger area, the strength will decrease as the square of the distance. Are you with me on that? It's called the inverse square law. So if you Google, we have tools that I didn't have when I was your age, right? We didn't have all that. There was no internet. No, there was no. It was maybe the beginning, but not like that. So you are so lucky. We didn't have, like, it was the time where you want to find a cosine or a sine or a log, you had to use table. And that's how old I am. So anyway, this is the inverse square law. I hope you can understand, right? You have a source of light, so you can have energy being spread out in space. So it's going to travel in space. And let's say you have a unit area here. So that could be a sensor. You know the sensor that you have, like light sensor, or to detect the amount of light going through. If you multiply by 2, the same light will spread over 4 times the area. Does it make sense? You don't need to take physics for that. It makes sense, right? So if it was, for example, butter, you know, like sometimes this is very unhealthy, never get that, but the butter spray. So if you have a French toast here with a thick layer, if you multiply the distance by 2, the layer here will be divided by 4. Does it make sense? And multiply by 3, it will be divided by 9. That's called the inverse square law. Radiation works the same way. So if you have a piece of uranium or plutonium or whatever, as you move away from it, radiation is going to go down very quickly. So that's why during World War II, when they were secretly working on the plutonium bomb, which is a very dangerous bomb, there was an accident because the guy, it was a group of young men, very passionate, and one of them was working on the core of that plutonium bomb, and by mistake, he kicked out the brick that was protecting the core, and he was exposed to all the radiation, right? But his friends who were further away didn't get anything. He died from radiation sickness. You can look him up. That was the first time that someone died from radiation sickness. You don't have time to get cancer. You have so much radiation going through your body, all your cells died, and you're gonna have like a terrible effect. And he was so passionate about science that in a notebook he wrote down everything that will happen to him. So it's like radiation sickness is like chemotherapy, but on steroid. Like you lose your hair, I mean, it's terrible. So anyway, I'm taking a tangent here. So everything to say that even radiation will follow an inverse square law. So this is let's say this is the Earth, you are on Earth here. So this is the surface of the Earth. You are 400 pounds on Earth. If you move away from the Earth at a distance twice the radius, what's going to be your weight? Instead of being 400 pounds, you will be 100 pounds. Excellent. And if you are here now, you will be 400 divided by 8. 90 pounds. You will lose weight, but you won't lose mass, obviously. Okay, so that's how inverse square law works, right? If you want to do a demo, it's very easy. If you are in microcontroller, for example, you can buy like Arduino, they have light sensor. You go from here, you collect the light and you multiply by distance by 2. You should see that light will be divided by 4, the amount of light that you collect. And it's very cool because you can connect that to your computer. You can do Python. That's another tangent. So let's go back to here. Okay. Now, let's connect to math. Let's see how is your math skill. Not even calculus. Let's look at your algebra. You have a function and it's minus 1 over r. Forget about that constant. Okay, so it's like minus 1 over x. Can you make a graph? Potential versus x. So minus 1 over x, what it looks like. Can you draw that on your notebook? Okay, so u equals minus 1 over r, whatever. We don't care about the whatever. What it looks like. Minus 1 over r. Remember that any function you want to go to the extreme. What's going to happen if r is really big? What's going to happen if r is very small? So if r is very big, what it's going to be? 1 over infinity is 0. Very good. Is it positive or negative, this value? Negative, so I should be here. And then 1 over something very small, it's going to be very big. So minus infinity, yes? So the function should go something like this, yes? Except that I'm going to be limited by the Earth radius, so that will be my distance r, but I cannot go inside the Earth, right? So I'm going to take here, that will be the radius of the Earth. Are you with me? So that will be my function. That will be the gravitational potential energy. You have to do it better than I'm doing, okay? For those who just came, I have chocolates for you. I try to buy only most healthy stuff. No palm oil, no canola oil, no coloring. Only European stuff. So okay, so that will be potential energy as a function of R. Do you agree? So how can I do at a given point? How can I find the restoring force, the gravitational force? What do? I need to find the slope because it's a derivative. And that will be my gravitational force here. That will be the slope. Okay, because the restoring force wants to bring the system to a lower state of energy. That's nature. Nature doesn't like to spend energy. It likes to have a lower state of energy as much as possible. And if we are close to the Earth, we're going to have that restoring force, and it's almost a line. Huh? It's almost a line. Do you see how here it's almost a line? Right? So we're going to see that. We're going to see that very close to the Earth, the potential energy will be mg r or mgh. Okay, so that will be h being the distance from the center minus the radius. Do you understand? Okay, so to make clear, if this is the Earth, right? So that will be r, so that's a distance r. That's the radius, and that will be your height. So if you are very close to the surface of the Earth, the potential energy is proportional to the height. Okay, so very simple equation. You cannot find something easier in that semester. You see I have a mass in my hand, and this is 2 meters. The potential energy will be equals to 2 meters times the mass times g, which is about 10, mgh. But you see what I like here is that you make the connection with the mass. The restoring force is always the slope of the potential energy. Isn't that beautiful? Yes? Okay. And it's if you are in chemistry, it's very important to understand that. Yes. U, it's the potential energy. Mu, it's the gravitational potential energy. Right? So it will be the potential energy. If I have my mass here, the potential energy of that notebook and the Earth combined, storing energy here, I can release that energy into kinetic energy. You see, he really wants to go to the lower state of energy, right? Oh, thank you so much. No, next. Okay. So if I want to finish my point. If I want to make my point, how do we connect with chemistry? So who knows that graph here? Have you seen this graph here? It's a very famous graph in chemistry. No? Sure. Yes, you did? Good. It's the Lennard-Jones potential energy. Have you seen that? You learn about that? Yeah, it's very good. So if you have a molecule, like with 2 atoms, if you try to break the atoms apart, you have a restoring force, right? It's not happy. If you want to squeeze them, they are not happy. They want to be at the right distance and then they will be happy. That distance is exactly the lowest state of energy possible in potential energy. That's what it says here, right? So if I try to squeeze them, it gets really, really, really upset. And then if I want to take them apart, it's going to be upset, but at some point, you can break. If you put enough energy, you can break and get them free. Does that make sense? So at a given point, the restoring force will be the slope. Okay? And it's a simplification, but it works great. Quantum mechanics, also you have those kinds of graphs. Okay, let's do something easy. Number 3. So you are taking a spring, but instead of going from not being stretched, you go from 3 meters to 7 meters. What's going to be the work done to do that? And that will be equals to the change in potential energy. So you are increasing the stretch. So you are doing work on the spring. So you are storing elastic potential energy. So do it, don't. It's not about the math here. It's just about how you're going to hide that, right? So potential energy at a position X will be 1/2 kx squared. So the change in potential energy will be, you see, 1/2 k x2 squared minus 1/2 k x1 squared. And that will be the work done. So be careful. Typical mistake I see will be to say, okay, I'm going to do x2 minus x1 and square. No, it doesn't work like that. Okay, so that will be 1/2 k x2 square minus x1 square. That will be the work done by you on the spring. Is that clear? Now, you could have used calculus, so the work done will be, by definition, the integral, okay, x sub 1 to x sub 2 of kx dx, because that will be the integral, and that will be x1, x2, 0.5 kx squared, and you get the same thing. Okay, so it will be the work done. And if you want to use a graph, we already did that last time, potential energy. No, that will be the force here. See, from x sub 1, we have chocolate for those who are late, even though it's not supposed to be late. So we did that, okay? So the force is linear, right? And if you want to find the work done, you find the integral. And how do we find the integral? You take the area of the big triangle minus the area of the small triangle. Remember, we did that. That would be simple math, right? Any question? Okay. Okay, so otherwise it's very easy. Okay, so the restoring force is said to be conservative. Why is it conservative? Because I never lose the energy I'm going to put in, for example, a spring. Because if I let go, all that energy is going to turn into kinetic energy. So this is called the conservative force. If I'm pushing a cart, for example, or for example, if you are driving a car, the engine is doing work on the car. Okay, so that work goes into kinetic energy. But if you apply the brake, that will be friction. Friction is not conservative. That means all that kinetic energy is going to be lost to heat. So friction is a non-conservative force. Agree? So close to the Earth, as I have explained, an approximation is that the potential energy, the gravitational potential energy is just mgh, and it always depends on your reference level. So I can decide to find the potential energy relative to the table, so that will be mgh, or the potential energy relative to the ground, or I can find the potential energy relative to the ceiling. So reference, it's up to you. Okay, so let's do something very simple. So potential energy depends on the reference level that you decide wisely to choose. You want to choose a reference level where the potential energy is zero, and that will make your computations easier. So you have to decide where is the potential energy zero. And we have chocolates if you want. I don't want to take my chocolates home because otherwise they're gonna melt. I mean, you can take two. Okay, so this is the ground. You have a table here. Okay, so 3 kilogram brake is lifted. Okay, so this is 3 kilogram. So then that distance here is 0.5, and the table here is 1. So first, relative to the table. So that means you decide that here your potential energy is 0. What's going to be the potential energy here? Okay, so you just have to find the height. So potential energy, it's always relative to what? Relative to the table. It's going to be what? 3, very good, times 0.5. Okay, so potential, I should say it's a change in potential energy is mgh. It's a change because it's relative to some reference level. Okay? Agree? So that's going to be 15 joules. Now, if you let go, all that potential energy stored inside the system Earth notebook will turn into kinetic energy. So you always get back your energy. Now, if you have potential energy relative to the ground, okay, it's going to be, so relative to the ground, now I have 1.5. So if I take potential energy equals 0, potential energy here will be at the height will be 1.5, agree? So it's going to be 3 times 10 times 1.5. Okay? So it's very easy. 45 joules. So potential energy depends on a reference level. We say that energy has to come from somewhere. So you are doing work against gravity. And then you can get back that energy. Good? Any question? So, yes. Okay. Okay, so that's also interesting is that, like, let's say you have two students and they want to go to here, which is lib 265, and you have two ways to do it. You can do it like me, right? Because I have to carry this bag, and you go straight up. But if you are in good shape, you can take a long way, and you can take the stairs. But in both cases, you start from point A and you end up at point B. So level, that will be, you start from level A and you go from level B. It turns out it doesn't matter what's going to be the path. It doesn't matter if you go straight up or if you go on the stairs here, or if you run to the library and then you come back and you go the stairs. The potential energy, and that will be true for any kind of potential energy, only depends on the initial point or configuration and the final point or final configuration. So it doesn't matter. In both cases, the potential energy or the change in potential energy will be the mass of the students times G times H. So let me ask you something. If you go up the stairs and then you go down the stairs, what's going to be the change in potential energy? Zero. That's also another property of potential energy. If you go back to the same position, there is no change in potential energy. So if you have a spring, you stretch the spring, and then you come back to the initial position, there is no change in potential energy. Yes. So but the total work will be zero because you do work against gravity, and then it's gravity that will help you. So even if you get tired, because it's a good question, because it's always the work done on, right? So there won't be the net work will be zero. So we go back to the dumbbell example. Even if you are tired, you lift the dumbbell, you lower the dumbbell, the net work will be zero on the dumbbell, by you on the dumbbell, right? Even if you get tired, that's the idea. But the net work done on the dumbbell will be zero, and you are going back to the initial position. Yes. Very good. Very good. Yes, exactly. So if the displacement is zero, the change in potential energy will be zero, and the total work will be zero, right? So I don't know if I have. Okay, so it says if there is a conservative force, remember conservative force meaning there is potential energy, then if the object goes around a closed path, then there is no work. The total work will be equals to zero. So the total work done by the restoring force will be zero if the object comes back to the same place. So it's one definition of a conservative force. Also, second definition, if you have a conservative force, the only thing that matters is your initial position and your final position. Okay? So it doesn't matter if you go from here to there or if you go from there to there. The total work done by gravity on that baseball will be the same because it only depends on the change. The displacement, you can think of that, the displacement, yes. Okay, so the path is independent. Okay, it's independent of the path. Okay, so the work done by a conservative force is independent on the path, and if you go back to the same place, the work done is zero. It's a lot of physics hiding in there. Okay, so what is true? Assuming that both students have the same mass, one is taking the elevator and one is walking up the staircase. It's C, very good. They both have the same potential energy, mgh, right? It's not that obvious. So conservative force, you can always get back the energy you invest in. Non-conservative friction, then you never get back. You lose. It's like Bitcoin, right? You lose everything. I don't know. I'm just kidding. My son is very much into it. I don't understand that, but you take a risk. Okay, you take a chance. So anyway, if you move something and you have friction, you go back to the same place. I can try to trick you. Then no, the total work will not be zero, because you cannot get back what you have lost in heat, for example, right? Or damaging the ground or the noise, right? So non-conservative force, it's going to produce heat. So anything that will produce heat is non-conservative. Is that clear? So a little bit of a teaspoon of calculus, not much. Okay, so I already talked about that in 1 dimension, but you can do it also in 3 dimension. The potential energy the force, the restoring force derived from the potential energy. So if you have derivative in one direction, what will be the opposite? Integral, very good. So if you have restoring force derived from potential energy, so the potential energy, you will need to take the integral. Okay? That's how it works. So for example, so when you go to maybe physics or engineering and you work on the very small, like quantum physics, like any nanotechnology, you're going to have to deal with electrons. So you can talk about potential energy, like in some kind of configuration. That will be the potential energy of an electron, of microelectronic device. In a microelectronic device, so we are dealing with microchips, microchips, for example. So where is the point where the potential energy is zero, for example, from A, B, C, D? No, the force is zero. The restoring force is zero. Remember, the restoring force is
D.
So D, yes, D is one of them. D is one of them. And A. Okay, so this is stable. The electron will be happy. If it try to escape, it can't. So we call that a potential well. It's trapped. Because if it try to go this way, you're going to have a restoring force because it's a slope trying to bring it back to here. If you try to escape that way, you have a restoring force pulling it in the opposite direction. Does it make sense? This is unstable because as soon as the electrons step on one side, okay, it's going to fall. Where do we have the greatest force? And that's not very obvious. The greatest slope here. What do you think? B, very good. So greatest force will be here. The slope, so that will be the slope, the largest steepness, and the force will be down. Okay, he wants to bring the electron down to a lower state of energy. Is that clear? So here that will be the rightmost point, right? With a force trying to bring it down to here. And then when you get to microelectronics or electronics, you learn that sometimes, even though the electrons it's supposedly not able to escape, sometimes it can. So it's called tunneling. That's how a microscope, microscope will work, right? So you see the electron here, it will be happy there. You see it has a lowest level of energy. Do you agree? And for some reason, there will be a probability where it can, out of nowhere. It's not making sense, but that's quantum physics. Quantum physics doesn't make sense. It will zoom, and then it will be happy because it will burp out energy. All the system wants to get to the lower level of energy. Isn't that interesting? So when you get to the very small, like the electronics we have in our laptop and everything, you enter the domain of probability. It's not deterministic anymore. That's it. Determinism is dead. You can only work with probability. And if you do chemistry, you learn that, right? When you have the orbital, you can say you have 80% of finding the electrons here, but you are not sure, 100% sure, right? And even in biology, when people learn about biology, it's actually all physics. It's all about electrons, electron transfer, right? So, for example, if you are oxidizing, when you are doing exercise, you are burning fuel, right? You are producing water and CO2. It's just electrons being transferred, which is very healthy. You don't want to keep too much electrons because that's when you get the free radicals. That's why exercising is very good. So anyway, my point is that when you get to a molecule size or DNA, for example, or small protein, you cannot predict. You cannot predict. It's not possible. Everything very small. At some point, you cannot predict what's going to happen next. That's another tangent. Sorry. So let's go back to business. Okay, the gravitational force. So can I say, let's see, I'll try to trick you. So you have force M1, force M2, they attract each other. Do you think that force F1 will be larger than force F2 because M2 is larger than M1? No, because of Newton. Third law, right? For every action, you have an opposite and equal reaction. So you cannot pull without being pulled. Yes.
But can you say that M1 is going to experience a larger acceleration?
Very good. Exactly right. So the force is the same, but not the acceleration, right? So the force will be the same, but the consequence is not. So even though the force is the same, M2 is very large, so the acceleration will be so tiny you cannot even measure it. And this one has a small mass, so you have a huge acceleration. Right? Yes.
Can you say that M1 is going to be experiencing a larger work than M2 because it's going to accelerate a lot more, covering a lot more displacement?
That's a good, but relative to each other, the distance will be the same. So when you talk about potential energy, it will be potential energy of the system. So both of them gonna lose the same amount of potential energy because it's M. Okay, it's a good question. I will look into that. I don't want to say something wrong. They will lose the same amount of potential energy for sure. Okay, it's a good question. I will get back to you. Want to make sure. So so the force, because we always say potential energy of a system, me and the earth, right? But it's a good question. Okay, I will get back to it. Okay, so inverse square law, right? So if you have a star, for example, and we talk about light, the same amount of light emitted per unit second, so that will be the power of a star, it's going to be spread out over a larger area. Okay, so that's why you have the inverse square law. So we already discussed that. Okay, gravitational potential energy, we just talked about that. So you see potential energy will be minus 1 over r. That will be at the surface of the Earth. It's negative. And as you move away from the Earth in magnitude, the potential energy is going to decrease at infinity. So if you are far away from Earth, it's going to be zero. There will be no force, right? And if you are very close to the Earth, it's mgh. If you are interested, you can show that here. You have to use an expansion, what it's called, Taylor series or something like this. You can do that. First, the slope is the restoring force, so it's a gravitational force. Okay, so the slope of potential energy versus distance is the force, the restoring force. It's a slope, the steepness. And you see that close to the Earth is almost like a straight line. Okay, so we already talked about that. That's the story of two atoms in a molecule. So if you try to squeeze them together, they're going to resist. If you want to pull them apart, they'll also resist. Okay, so we're going to define a new physical quantity. Oh, we went fast today. That's just for fun. Okay, potential energy, kinetic energy, potential energy. Can you do that? If you do that, I give you extra credit. But don't blame me, okay? I didn't say anything. Yeah. So you see, gravity is a restoring force because you can get back your potential energy. Potential, kinetic, potential. Wow. Given that you neglect air resistance and drag, right? So this is called conservation of energy. Okay, so that's
flaw.
So if you like physics, he's very famous on YouTube. I mean, he used to be a professor at MIT, and he was very famous to have those amazing demo. He stopped research just to invest in those demos. They are very famous. You can find them on YouTube. He got in trouble, but nevertheless, he's one of the best professors. It's a little bit advanced, but here I like that demo because he's really showing you that the force, what will be the force in that case? You have a spring and you have a weight here. So what will be the force pulling on the spring? Gravity, right? The force of gravity, right? And you're going to have a restoring force. And he's going to show you that twice the weight, twice the stretch. You can do those kind of demo, all you need to do is you go to the gym, you have those rubber band, maybe you have, 5 pounds, maybe 10 pounds, you should be able to see that the stretch will be multiplied by 2. A gym, especially because it's free, it's not free for me, they make faculty pay. Yeah, the gym. If I want to go to the gym, I have to pay, but it's free for you.
I have one here. It's not a very expensive
Not fair, right?
spring. You see
Maybe
it
I should
here.
cut that.
And there is here a holder
I have to edit
onto it,
it.
so it's already a little bit under stress. That doesn't make any difference. These marks here are 13 centimeters apart, and every time that I put 1 kilogram on, you will see that it goes down by roughly 13 centimeters. It goes down to this mark.
So twice.
Put another kilogram on, goes down to this mark. I put another kilogram on, and it goes back to this mark. All the way down.
So
and if I take them all off, so what I've done is I effectively went along this curve, and if I take the flaw,
see the curve here?
I have one here.
It's not so it's everything makes more sense when you do demo. That's why ideally for physics we should first do the demo and then the theory. So hydrogen, okay, that will be the potential energy. Do you agree? And that will be the minimum potential energy of hydrogen. So that will be hydrogen molecule, right? So hydrogen and hydrogen, that will be the ideal distance. If you try to squeeze them, they go crazy. Look at that. It's almost like a vertical slope. And otherwise, you really have to put energy to break them apart. right? You have to put a lot of energy to break them apart, and then it goes to 0, so the hydrogen are free. Okay. So let's introduce a new quantity, which is called power. So physical quantity, power is easy to understand. It's like metabolism. So that will be the rate at which energy is produced, the rate energy is consumed, and by definition, it's going to be the work divided by the time. Okay, so that will be the definition for average power, right? So something like our metabolism on average, our power production is 100 watts. So 100 watt means 100 joules per second. So we're going to produce as much energy in 1 second than a 100 watt light bulb. So question for you, how come if you are like a 100 light bulb, how come if I touch you, I'm not going to burn myself?
Sure.
Very good, because of the surface area. Okay, so it will be the same amount of energy, but it's spread out over a larger area. So that's why elephants, for example, they have bigger ears. They increase their surface area to to cool down more easily. Okay, so the unit is watt. Watt means joule per second. So even sleeping, you are producing energy, right? Okay, then so the definition of average power will be work divided by time. And work is force times distance over time. And distance over time is what? Velocity, very good, delta x over delta t. So another definition for average power will be force, if the force is constant, times the average speed. You can find, so this is average, you can find, so if it's gonna, you also have instantaneous power, okay, instantaneous power at a given time. So then you have to use the dot product. It's just definition, nothing to worry about, right? F and V are vectors. Okay, so units of power, 1 watt is 1 joule per second. Okay? For example, if you take the sun is losing energy every second, and the watt will be 10 to the 26 joules per second. Okay, so that will be the amount of energy produced by the sun in 1 second. Okay, so used to be, during the Industrial Revolution, they used to have a different unit, which is called the horsepower, because they were trying to convince people to give up their horses to move as a way to move from place A to place B, and to buy cars. So they got the idea, which is very smart, to compare cars and horse. So that's how they came up with the horsepower. So 1 horsepower is the power of a horse, and it's about 746 watts, about 1,000 watts, roughly. And you can produce 1,000 watts during only a short time, except if your name is, what's his name, Usain Bolt. That's very special, right? You can use power also, the unit of power, to compute, to have a different unit of energy, which is the kilowatt hour. So if you pay your electric bill, you're going to see how many kilowatt hour you have been using, but that's a unit of joules. Okay, it's a unit of energy. Sorry. Okay, so because of what? So power, can think of that as energy divided by the time. Okay, so I'm going to write it here, maybe. So power is in watts equals energy, which is in joule, divided by the time, which is in seconds. So you see that energy is the rate at which energy is consumed or produced. But that means that you can say that energy, let's say it's in joules, equals power, which is in watts, times the time. Do you agree? Okay, so energy is power times time. Now I can use a different system of units if power is in kilowatt, and now the time is in hour. So energy will be in what? Kilowatt hour. Okay, and that's how you can compute, if you buy a AC unit and it says, I don't know, I have no idea, 5 kilowatt. Okay, so that will be the energy consumed by your AC unit. And then you want to know, of course, in Florida, we want to use it for 24 hours. So the total energy that you are using will be 5 times 24 kilowatt hour, right? Does that make sense? So per day, you're going to use 5 times 24 kilowatt hour. And then for 1 month, so now you use every day AC. Well, we have no choice, right? Unless you like to sweat, which is fine. Sweating is good. You eliminate the toxin. For 1 month, that will be the total amount of energy. And then you Google it and you say, in Miami, what's the price of energy? I don't know. It's like, do you know the kilowatt hour? Look it up in Miami. 15 cents, something like this. 14 cents, it's very cheap here because they are using nuclear energy. It's very expensive. Hawaii, I think it has the highest rate. So 14 cents. So how much you gonna pay? 5 times 24 times 30 times 14 cents. How much is that in dollar? So that's per kilowatt hour. So how much do we get in dollar? 5 times 24 times 30 times 14 cents. Oh, it's expensive. 500 and $4. You see, AC, yeah? But I don't know. I say it's consuming 5,000 kilowatt. I don't know. What's a typical? Kilowatt? Small room or large room. Okay, it was not that far, right? 5 kilowatt. Small room will be less. Okay, so that's not that stupid. 5. Yes, entire time. Don't you? I do. No? Right? It's always on. I have to always on because my son has a Geico, like a lizard. So it's not going to be happy. No. Okay, it's a tangent. Okay, so but anyway, that's good because then, like, if you rent like Airbnb or whatever, then you know how much it's gonna cost you. So, okay, so try to do that. No, AC is very expensive. Okay, and especially if you have someone in your household that that is doing mining, for example, that's also consuming a lot of, like, they think it's free. It's not free. It's conservation of energy, right? So all that Bitcoin that you are mining, no, it's, you have to pay for electricity. Okay, I should definitively edit that video. So 800 watts, and the time is 2 hours, and the price is 10 cents per kilowatt hour. Can you compute? That's easy, okay? It's relaxing, it's not hard. So kilowatt hour will be power in kilowatt times the time in hours. Right? So the energy will be, you have to convert in kilowatts, agree? So it's going to be 0.8 times only 2 hours, just 2. So 1.6 kilowatt hour, right? And then it's 10 cents per kilowatt hour, so you're going to spend 16 cents, right? Okay, so that's easy. So now you know how to compute your electric bill. Okay, so next question. Okay, I'm gonna skip that. So horsepower, one horsepower is about 1 kilowatt. Okay, we can produce as much power as the horse, but in a very small amount. And here you have some examples there. Right, so for a flashlight battery, that will be 1 watt, 100 watt. That will be for us, for a human. So we are like a 100 light white bulb. If you want to power 1,000 houses, you need about 1 megawatt. So 1 million, you need 1 gigawatt.